look at Newton's law of cooling. So I wrote that down so I didn't have to write all that, while I'm trying to talk. And so the rate of change of temperature of an object is proportional to the temperature difference between the object and its surroundings, okay, or the ambient temperature. And that is, so if something's way hotter than, you put a very hot cup of coffee or a hot cup of water outside in very cold temperatures, it will cool down very quickly at first, because the temperature difference is so much. And so if we let U of t here be the temperature at time t, then what that's saying is U prime, the derivative, is equal to some constant of proportionality times U minus A. A is the ambient temperature or the surrounding temperature. Now, in the textbook, they go with, and this is reasonable, is if you're cooling, then, if the temperature of the object is greater than the ambient temperature, in other words, U minus A is greater than 0, then the item should be cooling down. Well, that means it's decreasing in temperature. That's a negative derivative. And so what is often done is we just assume K is positive, and then we rewrite this equation up here this way with a negative K, because we've assumed K is positive. All right, so that's what we have. And we're going to solve that using an integrating factor. And so to get it in the right form, I am going to multiply through by the negative K and move the KU to the left side, and then the KA stays on the right side. Now, we could do this by separation of variables. I could divide both sides by that. So I've got U prime over U minus A is equal to minus K. So, we might do this same model again in section 2.2, but for now, we'll solve it using the integrating factor. Okay. All right, so with our integrating factor, as I look at this, I see that my h of t is equal to k, the constant k, and so my uppercase h of t is e to the antiderivative of k dt, like that, and so that's just e to the kt. Now, so what I do again is I multiply both sides of the equation by h. So I'll get KHU equals KAH. Now, the whole idea is, again, this side, I'm not going to write out the e to the kt and all that, because this side, when I integrate then, this left side, I know that I'll just get u times h. That's the whole point. That is why we did this. We wouldn't do this if that weren't the result. So that is always the result. But on this side, where I've got KAE to the KT, I do want that because I'm going to do an integration. So when I do that integration, on the left, after the integration, I know I have u times h. And that equals the integration of KAE to the KT dt. So there on the right side, I'm seeing the integration. On the left side, I already did it. I didn't bother with the integral sign and all that because I know that's the answer. And so I have u, e to the kt, because that's what h is, equals, and when I do my antiderivative here, I get a e to the kt, and then plus my arbitrary constant. Now, well, now I can solve for u, and u is equal to, multiplying through by e to the negative kt, I get a plus c e to the negative kt. And now then, if I know that u of 0, if I've given an initial condition like u of 0 equals u0, under that initial condition, then I can place that in here. So I'd have a u0 there for u equals a plus c and e to the 0, but that's just 1, so I get this. Solve for c, that's c plus a is equal to u0. C equals u0 minus a. And so u is a plus u0 minus a e to the minus kt. Now, we'd need more information. We'd need another point in time to find k if it's not given to us. Okay? But there's our answer. I never have to do this again. Now, if I'm given an initial condition that's different than time 0, I would have to start here again to find c, or actually I guess start here again to find c, but I always have that answer right there. So it's really just a difference in the initial condition could cause me to get a c that looks different than that. Okay, but as long as I go with that, I'm good. Now, so they give us an example, 2.4, and this is sort of, a person, this is really, they never mention it, but this is the idea of trying to find time of death of a person, because we're told u of 0 is equal to 98.6 degrees Fahrenheit. That sounds suspiciously like the body temperature of a live person. Okay, but it's in an environment where the ambient temperature is 72 degrees Fahrenheit, and so what they would like to know is when is u of t equal to 80 degrees Fahrenheit. Now, the idea would be that if I can tell you what t is here, if it's 6 hours or 8 hours or whatever, that gives me a time of death, you see, is that if someone dies at 98.6 and we've got this model and we plug in the 80 degrees, then then I can solve for t and tell you whatever that t is. Well, that's how long they've been laying there. Okay. Now there's one problem. We don't know k. Okay, well, that's a pre-calculus problem. They had to give us some other information. They either had to tell us k or they had to tell us how to find k. Well, they give us a pre-calculus sort of problem, and they tell us at 3 hours it'll be 94 degrees Fahrenheit. Okay, so now I can use this to find k. I just plug it into my situation there, so u of 3, which is 94, but is also equal to a, which is 72, plus 98.6 minus 72 times e, and again minus k, but times 3. Okay, so I'll rewrite this as, I'll go ahead and subtract the 72 from the 94 and get 22, but also do this subtraction. I get what? 26.6 e to the minus 3k is equal to 22. So e to the minus 3k is equal to 22 over 26.6. that says minus 3k is equal to the natural logarithm of 22 over 26.6. And so k is equal to how do I work? Negative 1/3, I guess. Natural log of 22 over 26.6. Well, I have no idea what that is, but I do have Desmos up on my computer. And so let's see, 20 minus 1/3. Yes. So let me get that in there. So I got to type all that, and let's see, minus, and then divided everything by 3. It looks like that's about 0.4. 0.400489. So I could go, way back here to that, 0.005. I don't know. I haven't looked at what the book uses, but so we've got K, and hopefully I did that right. We'll look in a minute. So we have that. So now I'm ready to solve for t, okay, because I can go back here and use this, but now I know k. So actually I'll kind of use this thing here, sort of, in that, right, I want to find u of t equal, what do we got there, 72 plus 26.6 e to the negative 0.4005 t, but that's equal to 80. Okay, so that means 26.6. So you see we did the calculus and the differential equation stuff once, but now it's all a bunch of algebra stuff. Equals 8, and so e to the negative 0.4005 t is equal to 8 over 26.6, and so negative 0.4005 t is equal to the logarithm of 8 over 26.6. And so t is equal to minus the logarithm of 8 over 26.6 divided by 0.4005. So, what the heck is that? Well, let's see. 0.4005. 8 over, let's see, did I forget? I think I got a wrong answer because I don't remember what theirs was, but I got about 3. Okay, what did I do? So let me pause this so I don't sit there looking for a while. Let me a minute. Okay, sorry about that. What I did, I had a typo here. I didn't actually do 22. Sorry about that. Bad fingers, I guess. So this is 0.063. And we'll maybe 3. We'll go that far. And so 0.63 633. So, you know, everything's fine. I just can't type, I guess. So I'll get rid of those. Get the right one in there. And 0633, 0633, 0633, 0633. Now let me try that. Again, I'll type that in 0663, and I get T equals 18.12 hours. That sounds much better. I had gotten T near 3, and I thought, well, that's got to be wrong because that was 94. Well, yeah, so I typed in the wrong number. So at any rate, 18 hours, and let's check theirs. Then find. Oh, well, interesting. Oh, well, hopefully I didn't do that. I don't think I did, but notice there I've got I'll look again. 0633. I got 18.12. I'm guessing I typed something in wrong again. Let me see what I typed. Oh, yes, I typed in 0663 instead of 0633. And I should have gotten, 18.98. And that is what they have. So if I can learn to type, I can do what they did. But so that's the idea. So I'm sorry I can't type, but well, you know, that happens. And but that is the structure of this whole thing, and so you know, if I'd gone without a calculator, I guess I'd have been better off. But it is kind of nice to know what that actually, you know, comes out as. And so if you want to know that, you know, you do need to be able to put the numbers in correctly into the calculator. So anyway, so that is example 2.4. The big takeaways again from this example are I don't have to come up with that differential equation, or well, the solution to that differential equation again. I did it once. That's the solution in the general case. Again, the only difference would be, you know, if I don't have an initial value at 0, but an initial value at a different time, then this function would look a little different. But, you know, if I have those same situation, there's my function. I don't need to do any more calculus. It's all a bunch of algebra and key input into the calculator. Well, you know, that's where I guess I have trouble, but you all hopefully would do better than me. All right, so there's there's Newton's law of cooling and example 2.4.